Dynamic equilibrium. So, this is revision of year 11, or year 10 really. If you think back to year 10, just after rates, you started to talk about equilibrium. And you have etched in your brains that if you change the conditions of a dynamic equilibrium, then the equilibrium shifts. Okay, does that ring a bell? And also you'll start having little neurons firing, thinking about the name of the person who had a principle about this. Le Chatelier. So the idea here was that if you change the conditions, the equilibrium shifted in order to try and reduce the effects of your imposed change. This was an empirical law. It's something that Le Chatelier noticed with equilibria. So, without necessarily understanding exactly why it was happening, he could see that whenever he did this, whenever he changed something, the equilibrium shifted to try and reduce the effects of the change. Another phrase that will stick in your mind is optimum conditions. And optimum conditions in industry obviously are the perfect conditions to get a maximum yield. Remember, we don't do anything for fun. We do it for profit, do it for money. So you'll play around with the temperature and the pressure and the concentration of your reactants in order to get maximum profit, maximum yield, maximum products, essentially. Okay, let that kind of bounce around your head for a second. Temperature, pressure, concentration. Pressure really is concentration in gases, so as we'll look at again soon. Now, we've talked about the equilibrium constant at the end of, well, it was topic 9, wasn't it? Or was it topic 10? Topic 9, topic 10, topic 10. Yes, topic 10. So equilibrium 1. So, you know this already, but just a little bit of a recap. If you have a system at equilibrium, you've got the reactants A and B, products P and R, and then these little letters are the stoichiometric coefficients. So the number of moles of A, number of moles of B, etc. Okay? So the equilibrium constant concentration is, well, it's the products in the numerator, the reactants in the denominator, and it's the concentration of the product to the power of the stoichiometric coefficient. Okay? These square brackets mean concentration. Concentration in moles per decimeter cubed. So, a few notes to back this up. I've probably mentioned this already. The symbols always refer to the concentration of the species at equilibrium, and it's in moles per decimeter cubed. Convention places the substances on the right-hand side of the numerator, so products in the numerator. All substances present in the equilibrium mixture must be included unless they are solids. Okay, so if we're talking about concentration, we can talk about concentration of liquids, solutions, gases, but not of solids because they're considered to be constant, so they don't change. Kc is for a specific reaction, and you must quote the reaction. Interesting. It's a constant. We call it the equilibrium constant, but it's only constant if the temperature is kept constant. Kc, this constant, is temperature dependent. So if we change the temperature, we change Kc. Kc will be constant regardless of the initial concentrations of reagents, but if we change the temperature, then Kc will change. We'll look at this in more detail. Okay, so if we change the concentration of something, Kc, spontaneously, the equilibrium readjusts to keep Kc constant. It might take time for the equilibrium to be re-established, but eventually it will, and Kc will be respected. the units of Kc, obviously they'll depend on how many factors we've got in the equation. So if we look at the Haber process, then you can see you have 4 moles of reactants, 2 moles of products. So write an expression for Kc and determine the units of Kc in this case. So you need to think about what the expression of Kc will look like for the Haber process. Okay, so obviously you've got 2 moles of ammonia in the numerator, and you've got 4 moles of reactants. So you're going to have a Kc in this case, which is going to be square brackets concentration of the ammonia to the power of 2 over square brackets concentration of nitrogen, square brackets concentration of hydrogen to the power of 3. This gives 2 residual lots of units in the denominator. So the units here will be moles to the minus 2 decimeters to the power of 6. Now, if that's confusing to you, well, we'll come back to that and how to calculate it. But just have a little go, just to make sure that you can see that. Okay, if we want to find out what Kc is for a given experiment, a given reaction, then we have to have some way of finding out the concentrations of the species once equilibrium is reached. So what we do is we allow equilibrium to be reached, and then we suddenly lower the temperature of the reaction mixture so that we try and freeze, not literally freeze, but we try and stop the reaction so the equilibrium position is frozen while we determine the concentrations. This is one way of doing it. So suddenly we take the temperature down, and by kinetics we slow the reaction, and then we find out what the concentration of one of the reactants or products is. Let's have a look at a specific example of how to do this. So consider the reaction. Well, this reaction here is most probably quite familiar with you now, familiar to you. This is ethanoic acid, ethanol reacting this esterification reaction to produce ethyl ethanoate and water. Okay, you can add the state symbols here, but essentially you've got liquid. These two at the beginning will be liquids because you're mixing potentially two pure substances, so they're liquids too. And this also at room temperature will become a liquid, ethyl ethanoate. Okay, so we can consider everything in this particular reaction to be in the liquid state, especially if we mix these two together at the beginning. They're both liquid at room temperature. Now, what we do is we mix the acid and alcohol. We heat under reflux for several hours, okay, because organic reactions are slow. Then we cool the mixture in an ice bath, so that because it's such a slow reaction, if we cool it, then we effectively stop the reactions, the forward and reverse reactions. Because remember, forward and reverse reactions are taking place at the same rate. That's the essence of dynamic equilibrium, isn't it? Dynamic equilibrium. So dynamic equilibrium means that forward and reverse reactions are happening at the same rate. That's the dynamic bit. But at any moment in time, the concentrations, or over time, the concentrations of the reactants and the products remain constant. So if we allow this equilibrium to be established and we suddenly cool it, then we get a snapshot of what the concentrations are at that moment in time. Okay, what we do is then we titrate the mixture with sodium hydroxide. Sodium hydroxide obviously is an alkali, so it's going to react with the ethanoic acid. We can find out how much ethanoic acid we've got, and from that we can work out how much of the other substances we've got. Now, this sounds quite complicated, but we're going to work through it now together. Just as a little side note, if we mix a little bit of water with ethyl ethanoate and leave them or reflux them, they will they'll form these, and you can establish equilibrium from the other direction. Okay, so we mix 1 mole of ethanoic acid and 1 mole of ethanol, and we heat them under reflux for several hours. Just out of interest, how do we measure 1 mole of ethanoic acid? It's a liquid at room temperature, as is ethanol. How can we measure out 1 mole of it? Any ideas? Okay, it's a liquid, so we could find a volume of it. But what's the mass of 1 mole of ethanoic acid? Well, quickly add it up. Pause me for a second if you need to do the sum, and for ethanol too. And you'll find that the answers are, I think, 60 grams per mole for ethanoic acid and 46 grams per mole for ethanol. So we'd need density, and then we could work out how much volume we needed of each of these two liquids. Okay, reflux for several hours because organic reactions are slow, and then we need to stop the reaction. Okay, we need to effectively stop it. We're not going to be able to stop it completely, but we need to try and slow it down so that the rates are insignificant. So we pour the contents into iced water, and then we make up the solution to 1 decimeter cubed with cold distilled water. This also rapidly reduces the concentration, so also will slow the reaction. Okay, so we're trying to take a snapshot. We take 25 centimeter cubed of this solution, and we titrate it against 0.3 molar sodium hydroxide. And the titer is, or the average titer, no, sorry, yes, the average titer, we could work out an average titer. We'd have to be quick though, is 27.5 centimeter cubed. Okay, so let's go through this step by step. Let's walk through this and pause if you need to do the working out. Okay, so this is the beauty of a video. Just stop me while you're working it out. So the first thing to do is calculate the number of moles of sodium hydroxide used. Now obviously we're going to use this data here. Okay, and that should be your answer. Step 2. Now calculate the number of moles of ethanoic acid in 1 decimeter cubed. Well, it's a 1-to-1 mole ratio, so the moles of acid in 25 centimeter cubed must be the same as above, 0.00825 moles, same as the sodium hydroxide. So in 1,000 centimeter cubed, obviously we scale this up and we get 0.33 moles. What does that tell us? Well, that tells us that we had that many moles of ethanoic acid in the reaction mixture. So the reaction, or the reaction vessel with an equilibrium of these different substances, we had 0.33 moles of the acid. So this is the reaction, and like we said, we've let it reflux and the equilibrium's been established. But this format is something we're going to use in this type of question. So we'll look at how many moles we had of each of the reactants and products potentially at the beginning, and then we see how many moles we've got at equilibrium, and we can use the information for perhaps one of these substances at equilibrium to deduce how much of the other substances we've got. That's the plan. So we know at the start here we had 1 mole of the acid, the ethanoic acid, we'll call it the acid, and the ethanol, the alcohol. At equilibrium at the start we had 0 moles of the ester and 0 moles of water. at equilibrium, we've worked out that we had how many moles of the acid, if you look back to the last question. So step 3 is you have to calculate the number of moles of each of the species at equilibrium. We know the first one. We know that we've got 0.33 moles of the acid. So have a go at calculating the other equilibrium amounts. So yes, you've probably worked out that we've got 0.33 moles of the alcohol, because obviously the same amount has reacted, the same amount has been left over. Now the key now, this is the fundamental question. This is how much we've got of these things at equilibrium. But the question is how much has reacted between the beginning and equilibrium. And here, obviously, you do a little subtraction, you get 0.67. So if 0.67 has reacted, and this is a 1-to-1 mole ratio, then you can deduce that 0.67 moles of the ester have been produced, and 0.67 moles of the water. Once we have this, once we have these equilibrium amounts, we can work out our Kc. Let's have a go. Calculate Kc. So Kc is the concentration of the ester, the concentration of the water, the concentration of the acid, concentration of the alcohol. Okay, great. Now, you will be asking yourself, how come this is a concentration when it's really just a number of moles? How can we call this a concentration if it's just a number of moles? But this is a special example in that all of these substances are in the same volume. Okay? So if we want a concentration, we have to have moles per decimeter cubed. So moles over volume. But because we have two terms in the numerator and two terms in the denominator, then the volume terms cancel here. So it doesn't matter what volume we've got, the volume terms cancel. Okay? Or you could say, well, we made it up to 1 decimeter cubed, didn't we? So if we made it up to 1 decimeter cubed in the procedure, then 0.67 moles divided by 1 is just 0.67. It's another way of looking at it. We do that calculation, we get an answer to two significant figures of 4.1. So that's our Kc. What are the units here? Or the units, if we've got two terms in the numerator and two terms in the denominator, the units actually cancel. So here there are no units. All of these little details you should be writing down on your PDF document as notes. Okay, this is an interesting little table. You can see that the first line, we've just done that. I've just done that for you. So you can work out the Kc's for these different lines, these different equilibrium concentrations. Okay? You can use the figures. Now this is interesting. Some people in the past had decided that they'd made a mistake in the table, that these two numbers should be the same. I hope it was a pupil and not a teacher. So they've changed this to a 0, but this isn't a 0, this is a 1, 1.15, which you'll see when you do the calculation now. Kc, and we're going to assume that here we've been given concentrations in moles per decimeter cubed. We're working with 1 decimeter cubed of solution. So we put the numbers in. Let's have a look. Let's which line do we use? Let's use this line, this second row. If we put the numbers in, that's what they look like, and you get an answer pretty close to 4. So even if we've got, and this is the point, even if we've got different concentrations of reactants and products, it doesn't matter. If you give the reaction a chance to reach equilibrium, then the equilibrium constant Kc will be 4. Okay, we'll be doing that. We'll be doing this reaction. You can actually work out the Kc for this reaction, following the procedure more or less that we've explained. It's a good moment to just stop, take stock, read the pages and try the questions. There's plenty of questions on page 11 for you to be getting on with.